about rationality and unirationality and many other aspects of the problem. So I will begin with the history of my connection to rationality. So I started to think about rationality because Shavarevich asked me to look at the article of Katsila, and for the topic on rationality of the quotients of PGL2, PGL2 quotients of linear representations. And so Katsila published an article. And while looking at it, I found that his proof contained a mistake, which was later repeated by many other mathematicians, including myself, in many situations. That instead of a vector bundle, he was looking actually at a generic conic bundle, and generic conic bundle certainly has no section. And hence his first article on the topic was incorrect. And when I pointed it out to him, he was first he denied it because he had a explicit section, as he told me, but then in a week he realized that it was not true. And in fact, a week later he produced a correct proof, which was based on the following general principle, so-called GH section. GH section principle. Which works for arbitrary groups. So if you have, and especially for Lie groups. So if you have the action if G acts on X, generally X will be linear space and G is a Lie group, and then we call Y in X GH section if Y consists of points invariant under H, invariant under H, subset G. So H of Y is equal for Y in G. H of Y is equal to Y for Y in X, in Y. Yes, and so now the set Y, the Y is invariant, set of all invariant points. Y is invariant under normalizer of H. And then we have the following property. So definition. So Y under the above conditions is GH section. If G of Y is well, birational to X. That means it's an open subvariety in X, which is obtained by taking the orbits of Y. In this case, we have we have what we have is, I am dealing, you can define it at any variety, but C of y invariant under n of h will be birational. The field of invariance of y under n of h will be equal to C of x of g. So G invariance will be the same as C of x. Yes. And in fact, Katsila used it in his first proof to get rationality for the action of PGL2 for almost all representations. And he got it in the following simple way. So if you take, so it's the best way is to look at linear, when X is a linear space. X is, assume X is a linear space. Then what we have is that, so and both, and y is also linear, and so since we assume representation to be also linear, y is also a linear subspace, then we now can reduce. So if we have such a situation and y is g of h action, then we can analyze the action of a smaller group on y. And a particular case for PGL2 is the case of representation V4. That's where you can solve the representation of SL2 on polynomials of xy of degree 4. So dimension of E4 is 5, and it has a very particular GH section, namely, so E4 has Z2 plus Z2, so PGL2, Z2 plus Z2 section of dimension 2, section R. Dim R is equal to 2. Okay, I'll erase it. Yeah? It consists of Z2 plus Z2 invariant polynomials, so homogeneous of degree 4, and hence, which is clear that it is x squared y squared, and generated. So it's dimension 2, and the action Z2 plus Z2 normalizer of the section, normalizer of Z2 plus Z2 in SL2 is in PGL2 is S4. So therefore, and naturally, in this case, in this particular case, it's clear that R by S4 is rational. But in fact, it was clear from the very beginning. But we want to use the following fact. assume. So now, in order to apply, so this is a trivial case, but now in order to apply it to the general case, we can say that we can induce a GH section, namely if Z, so we have X, Y separately, and now if Z has G map Z subjective onto X, F, then F1 minus 1 subjective, and F minus Y of Y is also GH section in Z. So let's call it U. And then what we have to understand is that now we can reduce the case Z by G is rational, is birational too. And so this is a general fact. And now we would like to apply to a very particular case of PGL2 and linear representations. And in that case, we have to, if we look at the representations, so we need to consider, since we are looking at PGL2 simply, because we are looking at PGL2 because PGL2 is more difficult than faithful action of PGL2 is more difficult than faithful action of SR2. I will mention it maybe later, but we want to use natural quadratic map of representations to the above representation before. Namely, if we take S2, so what means quadratic? S2 of V to M, then it decomposes. It is, so to get a quadratic G map, we have to consider V to M, so the manifolds of degree to M, and then symmetric power, second symmetric power, is decomposing into a sum. And I think it begins V4 plus V8 and so on. So in principle, we know that tensor product, and I think V0, so V0. So this part is the one which is important. So we want to look at projection to V4 and get a image. So we take projection. It is a family of quadrics. So this is a quadratic map. So this map, this linear projection here defines a quadratic map. And the preimage of R, so the preimage F, which is G map in this case, and F minus 1 of R is the intersection is, let's say, I will call it 2, 1, 2, 3, intersection of 3 quadrics. Okay, so the intersection of 3 quadrics, and this intersection of 3 quadrics we have to divide. So we obtain that S2, that V to M divided by PGR2, since SL2 acts, effective action is actually PGR2, will be equal to Q123 by S4. It is very easy to see that division by S4 of a linear space, at any representation of S4, the quotient is actually rational. But however, here we don't have a linear representation. We have representation on the intersection of three quadrics, pre-image of R. Yes, pre-image of R. And however, at that time, Katsila made a direct computation which showed that in some direction this projection is simply so he reduced to some linear case, but that was made by their computation at some point. So later I started to think about how to do it in a more kind of theoretical way. And what happens here, and what happens also in many other cases, in some other cases, let's say not many, that these quadrics are very particular. Namely, there is quadrics, which intersection is Q123, contain a big linear space. I won't get into the Canadian journal, in Canadian notes, or somewhere, volume of some conference of Canadian Society, I think, that contains a big linear subspace. Which is invariant under S4. And then, in fact, what we obtain is so this is a subspace L, and what we obtain a natural projection onto a linear space, since it is an intersection of quadrics. So for each line, you have one extra point of section, so that the Q123, in fact, on Q123 happens to be equivalent S4 on equivalent to the action of S4 on the linear space, which proves rationality, hence rationality. Now this, in fact, this J.H. Jackson, especially in the case of big continuous Lie groups, works kind of at least provides many equivalences. So in particular, if you have G is a linear group, if G is a connected Lie group, and then we certainly have that G acts on the algebra, on G algebra G of G. And in case of semi-simple groups, we in fact obtain so we have a natural G section, which is Courant subalgebra. So Courant subalgebra is a natural G And here I would say n of t section for n of t section for the action on G. T is a maximum torus, maximum torus on G. So in some cases, this actually gives kind of reduces theorem to the kind of toric action. So it reduces theorem to the problem toric actions, not linear actions on of the groups of the group of the Weyl group of the Weyl group of G, or some kind of central extension. So what is certainly for Weyl groups, we have a classical theorem of Chevalier. I just want to remind it. Chevalier, that for linear action of V of G with generators which are reflections in hyperplanes, and actually means like, for example, like T tangent sub-algebra to T has rational quotient. That's a theorem, basically pure computation, but beautiful computation by Chevalier, which was kind of a fundamental in this at the beginning. Yes. So that's groups generated by reflections or pseudo-reflections, I think also give you rational quotient. However, the action of n of t is more difficult. In general, since first we don't know, for example, even for linear actions of Chevalier groups, but for bigger linear actions, where the elements of the standard reflections are becoming simple elements of order 2, for example, symmetric power of the second symmetric power of the standard representation, is already a question, I think is not really solved for many groups. So rationality is kind of difficult property, and I think even for symmetric group we don't know much about rationality of the higher degree representations for symmetric group. But here the situation is more difficult, because certainly if we have action n of t on V linear space, then in fact we have action of, let's say, I would say V of G on V divided by T. which has natural toric structure. Since T, the action of T on V is diagonalizable, and hence we obtain a torus, quotient of a torus in V divided by T will be torus, and we obtain a toric action. So hence, we cannot conclude rationality. And toric actions are kind of more difficult. And rationality is established in some cases, like for many burning, I think established using similar ideas. Burning and Shepherd Barn has established for some groups like SL3, or even some cases of high-dimensional group. Rationality by this direct method, but rationality is usually a difficult property. The simpler property is stable rationality. So stable rationality. And stable rationality so means that we take C of V, C of xg, and we want to say that it is stably rational. So stably rational if for some n we have C of x, g, x1, xn is rational. Rational means purely transcendental. Rational. When I say rational, that means purely transcendental. Transcendental extension of C. So there are here C. So this field is actually C of y1, yn, where there are independent elements. So after adding some x1, xn, and it was proved already then these two notions by a group of people, including Colette, Bouville, and some other, I don't remember names, that this property is actually, this rationality and stable rationality are different. What is good about, what is better about stable rationality? That somehow for stable rationality, we can, for stable rationality, we need basically to establish it for one representation. Okay, for stable rationality, so we have the following simple result, which appeared, I think, in our article, I think it appeared in my article, but actually people knew it. I think that I didn't even claim this result, and because it was known as basically Hilbert-90 theorem, or it's a theorem. In fact, I think that it appeared sometime, so it is kind of folklore knowledge, though I kind of proved it myself, but I bet it was pretty well known. The fact is the following: that assume that we have, so for linear action, so if G, if B is a faithful means faithful action of G, faithful algebraic action of G, and V is VI, let's say, faithful algebraic action of G for I equal 1, 2, then if C of VI, actually C is just any field, C of VI, G is stably rational, then the same holds for U2. And the proof is very simple. The proof actually is based on the fact that algebraic vector spaces, algebraic vector bundles or varieties are kind of linear, are birationally products. So in particular, what we do is we take product V1 cross V2 and we take diagonal action by G. Then it is a fibration with fiber, generic fiber birational by G over V1. So this is vector bundle, and this is birational vector bond. So vector bond on an open part of V1 by G, V2 by G. So here, certainly, the notion of a faithful is non-trivial. So just exact representation. That means exact for finite group. That means that generic orbit is isomorphic to G, but we need a kind of generic stabilizer is trivial. So generic orbit has to be isomorphic to G. That would be faithful action, not just effective action for that. So there is a difference, which is a slight difference in case of, let's say, linear groups. So standard action of SLN on V is for big N, certainly, how to say, every element acts non-trivial acts non-trivially. However, it is not faithful because the stabilizer of generic point is big. Of any point is big, though they differ. But for finite group, it's the same. So in particular, for many groups, we can somehow easily get representations where the quotient is rational, and then stable rationality is stable rationality for many other representations becoming trivial. So this certainly happens, for example, for groups, so-called linear groups. So for linear groups like SLN, JLN, SPN. So for this series, and I wrote it, but I also think it was well known that for faithful actions of this, that these groups by themselves have some kind of linear structure. So, and I want to say that, for example, SLN certainly acts on, how to say it acts, its action on itself, translation on G is equivalent to the vector bundles, X to the action on a tower, let's say, of vector bundles. So vector bundle over vector bundle and so on, and then over linear space. Okay, so first, and for all these three groups, they have this particular structure that their action on themselves is linear, and which implies, and in this case it is, so this makes it trivially stable rationality for faithful action trivial. Yeah, maybe I can give an example. Yeah. How, and the same, so for example, for the groups like V of G, so weight groups, since we have one representations like Sn or similar groups, since we have a representation by Chevrolet theorem, we have at least one representation where the quotient is clearly rational. We obtain that all of them are stably rational, but rationality is a difficult problem. Advanced technique, actually, I lectured about it on Wittenberg seminar, and after that we discussed with Katsila, and he came up with another proof, which was based on this fact for the rationality of PGL2. He managed to get kind of, so we talked about it a lot, and then he managed to get very clear decomposition of kind of vector band structure of a high dimensional representations of PGL2, so high dimensional representations of PGL2, and kind of projectivization of high dimensional representation, or as a vector bundle of projectivization of a smaller dimensional representation, and then from that rationality also for the quotient followed quite easily. And this actually, so it was interesting that the vector bundle techniques, so what I mean exactly for vector bundle is the following. So let's look at SPN. Okay. So SPN certainly acts, so it acts transitively on Cn, and then if we, for any x in Cn, there is a subspace which is kind of, there is a bundle, there is a phi by Cn minus 2 minus 1, and orthogonal kind of x, so omega xi equals 0, and so on. So so we have a sequence of bundle each time, kind of the trivial a product which is trivial with x, and so for any x we select such that all the correspond to omega is a form, omega 2 is corresponding form. Okay, and we have this kind of vector band structure. So which point it's which is SPN invariant vector band structure on SPN itself. We can approach, so here the same approach to SON, keeping kind of orthogonal subspaces, gives a similar structure. However, it tells you that there is Z2 N section. So it basically reduces to the action of abelian group. However, if you go to spin N, I think Z2N, I don't know, Z2N. Yes, if you go to spin N, the same action on kind of a bundle or orthogonal reduces everything, provides the action, provides a similar SON, spin N action, but here will be Heisenberg group, big Heisenberg group. And then, so we can therefore reduce stable rationality question, or at least rationality both and stable rationality question for SPNN to some very particular, to the action of Heisenberg group, namely, it slightly depends on the on the spin on the end, whether 2 divisible by 2n, but just Z2 extension. And then all of a sudden, this question is becoming difficult because so my direct attempt to do it kind of was, so I met a conic bundle, and hence it is possible to obtain the kind of, strangely enough, it's possible to obtain the smaller the smaller quotients of smaller Heisenberg groups are kind of described as conic bundles or quotients of a bigger Heisenberg group, but it doesn't help to disprove rationality. So in a way, this problem for big N, for n greater than 12, remains questionable. And there were some other cases which I looked at, trying to do it with vector bounds. Some were successful, some not quite, but at that time I kind of started to be interested in the question of abstractions to stable rationality. Abstractions to stable rationality. Rationality of group quotient. In fact, at that time, so it's again, it was kind of Shafarievich who asked me to talk about the work of Saltman on the topic. Saltman created, was first to create finite groups, a finite group is G is B by G non-stable relation. So with non-stable rational quotient. And that his article of 84, since I was I was given actually I think a series of talk on this article. At the same time, I tried to understand what's happening there, because Saltman used very kind of algebraic action. He talked about Brouwer groups of the fields, and it took me some, not such a big, but some effort to translate it into Bogomolov. His groups were of the type were just central extensions. So his first examples were of this simple type. Okay. Central extensions. And as I understand, in this case, he looked at but what he was discussing, in fact, after translation to algebraic geometry, are the elements of the type. So he computed he found an element gamma in H2 G by ZP, which is unramified. So that means the following, that if you have an element of the group G, and we have P by G, which is algebraic variety, so faithful action, and then so we have here C of P by G, and unramified. So if you take evaluation, take any divisorial evaluation, and V, and then V defines, so then certainly as usual, we have a divisorial for any divisorial evaluation, there is a decomposition group. Variation, actually in this case, for divisorial evaluation, decomposition group is simple. I will take, so this the inertia, which is kind of Z in this case, and the quotient group. So this is a group kind of talking about, maybe take completion here, and talking about Galler group of the quotient field. Okay, quotient field of the evaluation. However, in this case, what we are interested actually, so we are interested in, so we have an element H2 of G, and certainly G is a kind of fundamental group, so we can think G as fundamental group of V by G minus singularity something, so minus some small set corresponding to invariance. So I would say VL by G, so where the action is free. Okay, and then what we can get here is the following. What we can get is gamma, so we can pull gamma to this group here. And we say that gamma, certainly there is a cyclic central subgroup, central, so this is central extension. And more, it's like you can think about it as a product. It's not canonically a product, but as a product, it is a quotient. You can think as a product. And then we just induce gamma on this group. And so gamma, so definition, gamma is unramified if it is induced from gamma. So essentially it tells, so this is how it is, how people speak about it in algebra essentially, but in our case, that means we have V by G, we can think about it as a smooth, so we smooth it out, smooth, and we assume that there is a divisor with action of a stabilizer, so we have action on S, D, yes. So we actually have our D. We are looking only on such devices which are coming from SD by SD, D prime by SD divisor, a generic point. And what we want is our element gamma is suddenly defined well outside the divisor. So on points where the action is free. But then what we want non-ramified means exactly that we can extend it through divisor, through the generic point, extension. So through generic point of any device. This is simple property for, so in our case, when we are looking at H2, it's a very simple property. But so, and this is, so it's a simple property, and so essentially H2 non-ramified will be just in a subgroup in a cohomology of, so it is a subgroup of a cohomology of the smooth completion function. And this happens to be invariant of stable rationality. So it was shown essentially by Collier-Telen, that this does not depend on representation. So the fact that it doesn't depend on representation, and I also showed something in that direction. And then there is a precise computation, so we can actually compute it in terms of the group H2, and this unramified can be computed in terms of the group G, and this is so like that, sometimes called Bogomolov multipliers, but in general, in my article, it was like B0 H2 GZP, and this is exactly the subgroup of elements of G which are trivial on all trivial restrictions on all abelian subgroups. On all abelian, let me, so, trivial on all abelian subgroups in G, namely for any A, so gamma is here. If for any A, gamma is inside gamma in H2G. Let me call it Q by Z, since I just want to forget about some Bach-Stein type elements so that it maps to 0 in a slightly bigger coefficient group. So that group happens to be explicitly described in terms of G. And we can, by analog, we can define similar groups, just the elements which can get through, can be extended through any smooth point of any divisor on any model. And that's important. On any model, extending on any model is kind of different from just extending on one model. From extending on some particular model, it may not be expandable, but maybe on some other model you can do it. So that's a tricky, that's in fact becomes a tricky and a property in higher dimensions. If you look at, not at H2, but at H. What we're getting is abstraction to rationality. And this abstraction has to be non-trivial for, actually for a big class of P groups, so that after kind of a small correction given by Kang, I think, and Moscovici, I showed first, but then they corrected my calculation by 1 degree, so that already for P, for groups of order greater or equal to P5, I wrote greater P5, that proved that there are some groups like P5, we have finite P groups, I think P, right, P groups with non-rational, with non-stable rational quotients. On the other hand, for groups less than P4, so if order of G is less than P4, then the quotients are stably rational. I also remember that I think Kant in Korea and some other several other mathematicians worked on this problem and proved. So in some way, it is clear that the spectrum of non-stable rational quotients is quite big. Okay, so but on the other hand, let me go to another topic. On the other hand, we have the problem. So all these varieties are so-called unirational. So if you take V by G, then it is unirational. That means that the corresponding field certainly is inside C of V, and that means unirationality. So then I began to look at the property of unirationalities. Happens to be even more complicated proof, more complicated property than rationality, because in many cases, already for conic bundles on P2, it seems like unirationality is not well established, is not very well understood, and despite the fact that there are many, so by now we have many manifolds which are look like unirational or there was this property of rational connectedness, but its relation with rationality and stable rationality is still not clear. What I would like to discuss is some unirationality questions related to unirationality. We know that so X is so simple examples of unirational is certainly the spaces of types Pn of G, the quotient. So where Pn is a projective space. So Pn of G is, on the other hand, somewhat symmetric, has big group action. Big group action. And even the same, in fact, we can think about it as a quotient of projective group where the action of projective group divided by subgroup simply transitive. So on the other hand, certainly there are many varieties which are unirational, no, but not have no this group structure, group action. So, for example, if we take X3 is a smooth cubic in any projective space. So, in particular, if dimension is X3 is 3, then it is not rational. It's well known. On the other hand, I was thinking about the following alternative. That in fact, after stabilization, maybe so conjecture, and this is formulated in our paper with Kurchemanov and Koyumjan, that unirational maybe conjecture question, yes. Unirational maybe has a state model after adding several parameters, with infinitely transitive algebra with infinite transitive action of a group of algebraic transformations. And in fact, we proved something in this direction, but certainly not the complete conjecture. So it's still it's a question. Yes, it is not clear, in fact, how much it may help, because the group which act are not of Lie type; they're in fact infinite dimensional. So, for example, as a group of automorphism of T2 or CN or S algebraic, right? So AN. What I mean is the following: that when we add variables, we can do it in a more smart way. That means that if we take, for example, if you have P1, and certainly there is a transitive group reaction, but it is three transitive. So it can move any 3 points into any 3 points. However, if we take O minus 1, a bundle over P1, minus P1 itself, then you obtain C2 minus 0, where the action is infinitely transitive. Infinitely transitive. Transitive means any endpoint for any n can be transformed by algebraic transformation into any other endpoint. So X is called a manifold, non-projective maybe, but algebraic manifold with an infinitely transitive algebraic group action if any endpoints can be translated into any endpoints. This notion was introduced, I don't know, some time ago. I can't even quote who introduced it, but certainly it's I got to know it actually. I started to understand it after maybe Popov maybe introduced or some other people. Popov, Zeidenberg worked on it. So many people. Kayumjan told me that, and then I noticed that the following certainly the theorem we can prove is that assume that X of dimension n, yes, has n constellations. So that means X, C of Xn or K of Xn, doesn't matter, has a representation and C of Yn minus 1, I minus 1 of Ti for n different algebraically independent Ti in C of Xn. So that means it has a n what's so to say uniral structures, but on the level of fields, and we don't look at any. So what we know only that they are algebraically independent, but what kind of field they generate, we don't even know. So in fact, so that's the only condition. So they have to be sufficiently independent. Then, in fact, there is a model. Means algebraic variety mx, which is birational to C of x, y1, yn, some number of variables, some number I don't know, which has algebraic group of automorphisms infinitely transitive. In particular, X3 is becoming after, I think, x33 is becoming after adding two variables, if I remember correctly. So if you take cubic, which is unirational but not rational, of dimension 3, then after adding two variables, I think 2 is enough, we obtain an infinitely transitive manifold, a model. So it's an algebraic variety, not it's kind of almost, I think maybe it's affine, even I'm not sure it's affine. But there is an explicit, almost explicit construction, basically by taking kind of by adding this O-1 type for different directions, such that the resulting variety is infinite and transitive. So it's some kind of homogeneity, infinite transitivity in many cases. However, so and we did it for projective, for varieties of type En by G. Certainly, for varieties of type En by G, many hypersurfaces, many unirational hypersurfaces, basically hypersurfaces of relatively small degree in big dimensional projective spaces, and so on. So we gave many examples, but unfortunately, we, as we have shown in the article with Prokhorov, some natural candidates, some bundles, which some bundles with fibers which are not kind of projective spaces, stably not projective spaces. We couldn't do it, and there seemed to be, and at least our method didn't work in this case. But in this way, I just want to say that infinite transitivity is a very difficult property because this group is the group of automorphisms is far from being algebraic. However, at least it is, so that's why it's a conjecture question. Still, since we don't understand anything about unirational varieties at the moment, and unirationality seems to be by far more difficult property to understand than even rationality, it's wide open. Thank you very much for attention. Unfortunately, I won't be able to answer questions, but if you got some, please write me. Thank you very much.